All right, we're back. We are on, what are we on? Oh, we're on page 4 of, so I got a little distracted because we're going to paint the office. And so we had to spackle some stuff. And so if you're like really into looking at the background, that's what those marks are. Anyway, page 4, notes 3, Calc C, talking about sequences. We just talked about monotonicity. So a sequence is monotonic if it is non-increasing, meaning it always gets, the terms always get smaller or stay the same, or non-decreasing, which means that the terms always stay the same or get bigger. So monotonic is one idea, and we kind of like looked at the first derivative to tell us if a function was monotonic, or a sequence, I should say. We looked at the function that generates the terms of the sequence. And now this next concept we want to talk about is called boundedness. So a bounded sequence is, well, first of all, let's talk about bounded above and below. So a sequence is bounded above if this symbol, so there exists, because I don't know if you've seen that before. There exists M that is an element of the real. So you've definitely seen is an element of before. That's that weird E, kind of looks like a euro symbol, but a little more extended maybe, such that A sub n is less than or equal to M. So M is the upper bound. And then this symbol is for all. N. So what we're saying is that when you look at the terms of the sequence, so you have your sequence, so let's say this is like A sub n, and then this is n. So bounded above means that all of your terms, you know, maybe it's monotonic, maybe it's not monotonic, doesn't really matter, but they never get above that line. They can hit the line, but they're never going to get above the line, right? So that's what it means to be bounded above. There's a ceiling. It's never going to go above the ceiling. Bounded below is the same kind of idea, except it's a floor. So there's a floor, and you're never going to go below the floor. So this sequence that I've drawn is bounded. It's bounded above by this top line. It's bounded below by the bottom line. So you have a ceiling and you have a floor, but this is not monotonic because sometimes you're increasing, sometimes you're decreasing. But boundedness and monotonicity aren't like linked together. You don't need to have both of them. They're two separate ideas. So we have this concept of boundedness, which if you think about it, it's like a horizontal asymptote basically, right? So like as you go to infinity, do you have a horizontal asymptote? Or because it's a sequence and it can be weird, do you have like two of them, right? Like one above, one below. So that's the idea of bounded above and below. We'll say that a sequence is bounded in general if it is bounded above and below. So this idea is important, and we've seen it before, right? So when we had like 3 plus -1 to the n, and it was just spitting out 4, 2, 4, 2, 4, 2. Actually, I see that example down here again. I use that a lot. So it's just spitting those out. It's definitely bounded. It's never going to be greater than 4. It's never going to be less than 2. It's bounded, but it's not monotonic. So it's actually easier for a sequence to be bounded than it is for a function to be bounded, because you know you get those like weird functions where they're like this, and then you got your vertical asymptote in the middle, right? So if this is your function and your only terms of your sequence are this, then your sequence is monotonic and bounded. But if it's the function obviously, because it was like this, the function is unbounded because of the vertical asymptote. So because of domain issues, it's easier for a sequence to be bounded than it is for a function to be bounded, because sometimes you just jump right over those vertical asymptotes. It's kind of, I don't know, I think of that as a good thing. I don't know if it is or not. So the reason we want to talk about boundedness and monotonicity is so that we can combine them into this basically. So if a sequence is bounded and monotonic, it definitely converges. Because like, how could it not? It's like it's bounded, which means there's a lower bound and an upper bound. It will never be lower than the lower. It will never be higher than the upper. But it's monotonic, which means that it's always like approaching the ceiling, or it's always approaching the floor. It must converge. It converges to the ceiling or the floor. Then you get into this idea of like a least upper bound and a greatest lower bound. So for example, in this little picture that I made here, this is like our least upper bound. There's other upper bounds. I mean, like it'll never be bigger than this or whatever, right? So there's a least upper bound, and then there's a greatest lower bound. So greatest, when I took a course called analysis in college, this, a lot of people had trouble with this idea. Oh, are you not gonna straighten out? I thought that would just become a line for me. There we sort of go. So that's my greatest upper bound. Greatest lower bound, least upper, greatest lower. That's my greatest lower bound. So there are smaller lower bounds, but that's the biggest one that works. And that's not an idea that we really need to worry about, but it is a thing. So here we want to do determine if the sequence is monotonic, then if it's bounded monotonic. So first, is it monotonic? So for A, we definitely know this is not monotonic. I think we can borrow these answers from previous problems, perhaps. Not monotonic. It is bounded, though, right? Because this is the sequence that just keeps spitting out 4, 2, 4, 2, 4, 2. So it's not monotonic, but it is bounded. It doesn't converge. Let's see, B. So we have n over 1 minus 2n. I feel like, have we used that before? N over, okay, so we did the work, right? So from the previous page here, we know that this is in fact monotonic. So I'm gonna say is monotonic. Now, I kind of need some of the terms. I'm just gonna have the calculator spit out the terms right now because, I don't know, I feel like this video is already going long. Kind of like mindlessly long though. And also like, this isn't even an idea that we talk about all that much. So I'm going to define a function a of n, and I'm going to say it's n over 1 minus 2n, and then I will generate the sequence a of n, comma n, and I'm going to go from 1 to, I don't know, like 5 or something, and see if, okay, so key thing here, the smallest, it's always increasing because it's monotonic. And then the smallest it ever is -1. So this is in fact bounded. So let's go back and say we are bounded. Let's do this. I'm not enjoying the way this video is going. I might there's a chance I'll remake this. It is bounded. So the maximum, let's say the maximum, oh yeah, the maximum is less than or equal to -1/2, which is the limit as you go to infinity. And then the minimum, the floor, is greater than or equal to -1. So it is bounded, and it definitely converges, right? It definitely converges to -1/2. So bounded, monotonic and bounded definitely converges, which is kind of like the idea that we're going for here. This one I think we also did, so let's go here. This is not monotonic, so that's good. So not monotonic, because we already did the work on that. Is it bounded though? So I'm gonna let the calculator generate some terms for this one too. It's probably not the best way to do this. I mean, I really want to find like the maximum and find the minimum, but I also just don't really want to do that. So let's see, n squared over 2 to the n. I don't know if you can tell, these are like not my favorite notes to go through. They're the least applicable to anything like going further. I hate one-off topics, like they're so annoying. All right, we're gonna do a couple terms here. I don't know, like the limit is definitely 0 as you go to infinity. So yeah, so you increase. So let's do this. Let's do derivative a of x comma x. Oh, this one, right. I took a couple days off in between the videos, and so can we solve this? Okay, sure. So increases, let me see here. I think we increase such that x equals 1. Increase until we get to, yeah, you increase until you get to 2, to n equals 2. And then you're going to decrease after that. So if I do like 3, I should get a negative for my derivative, and I do. Okay, so the sequence increases until n equals 2. So a of 2 is the biggest that you're ever going to get. And then A of 3 will be smaller because it's on the other side. So this is bounded. It's bounded by 4/3, which is what you get. That's the top, right? So that is your least upper bound. Okay, so let's say we are bounded. How do you spell bounded? Bounded. Okay, so the maximum is always less than or equal to 4/3, which is A sub 2. And then the minimum is going to be the limit as we go to infinity, which is greater than or equal to 0. So you can never actually get a negative out of it. You only ever get, is that true? I don't even know if that's true. I did not investigate this enough. N squared, there must be a place where we like wrote those out. Yeah, you only get positives. So the biggest ever is 4/3, and then smaller and smaller as you go. There you go. All right. So this was not my best video, but I am going to wrap it up here and come back in the next one and deal with the rest of this page. And so I hope to see you there. So till then.